Hello, this is Dr. Keith Schubert, and we're going to take a look right now at floating point multiplication. So when we're looking at floating point multiplication, I've put in two numbers here you can see, and this is the format we use for recording them as we've talked about in the past. -1 to the sign of whatever the first one is times 1. Remember, that's our hidden bit, so I'm assuming at the moment that we're going to be using normalized numbers. If you have the denormalized, you just replace the 1 by a 0. So dot, right, so that's the radix point, and then f1 is the fractional part of the first, times 2 to the exponent of the first. And in this case, I'm assuming that we have the actual exponent of the floating point number, not the biased version. And I'll note down here at the end that, we're in general dealing with the actual biased one, so we'll have to remove that out. But let's just take a look at this part here. Assume we have the numbers in scientific notation. Same thing for the second one. -1 to the sign of the second one times 1 dot the fraction of the second one times 2 raised to the power of the second one's exponent. Since everything inside here is all multiplication, and we're multiplying the two numbers, it's just a whole bunch of multiplication. Multiplication commutes. That's actually not totally true. Floating point numbers you can show don't work, but in this case we can go with that it commutes. So I can group together -1 to the sign times -1 to the sign of the second. They have the same base, so it's the same as adding the exponents. Now we note that that is actually the same as doing an exclusive OR, and the reason is we only worry about the first bit. So if you do true addition and both of these are signed, you get 1 plus 1, which is 2, but 2 is 1, 0. We only want the unit digit, so out of the 1, 0, we only want the 0, the units 1. So that works out to give us XOR for that case that goes in. So we just have to exclusive OR the sign bits, and it will work for us, so that's nice. The significand, we're taking 1.f1 times 1.f2. So we're just multiplying those. Now I note here a possible shift, because if you've got two numbers here that are sufficiently large, it is possible that 1.f1 times 1.f2 could be 2 or larger. So you'd have 1, 0 dot something or other. Remember, we can only have 1 dot. So if it ends up being something 2 or larger, we're going to have to shift it back so it becomes 1 dot, but that means we'll have to alter this by increasing the exponent. So since we would be decreasing the number of digits in the significand, we would have to add whatever decrease we did there, we have to add it back in, so there's no net change into the exponent. So we note that there is that kind of possible shift that goes on. Then the exponents, we just add them. Now, since we're adding exponents, and we technically have them encoded with a bias, in the case of single precision, we noticed this was 127, we actually have the exponent plus 127 plus the second exponent plus 127. So now we got two 127s in there. So you get the exponent of 1 plus the exponent of 2 plus 127 plus 127. I need one of the 127s for the encoding style. So that's okay, but I have an extra 127, so there's just 2 of them. So in that case, we need to come back in and we need to remove the extra bias. So we take the encoded version of the numbers, add them together, and then subtract 127. And what that ends up giving us is the exponent in the excess code. So that's the basic idea of how you do the multiplication that's going on. So to make life easy, let's just kind of consider for a second a 4-digit decimal example that's going on. So this is 1.110 times 10 to the 10th times 9.200 times 10 to the minus 5. Same thing works here. We take the exponents and we add them. So 10 minus 5 gives us 5. We multiply the significands, 1.11 times 9.2. So that gives us 10.212. So you'll see here, this is 10. It's too big, we need to shift it over. But this is 10.212. They put in this extra times 10 to the 5th, they carry this down here so that when we normalize, shifting the radix point over, you see we decreased it here, so we had to increase it here. So they're just trying to let you see that they're coupled. So I just took that exponent and wrote it in, and then brought it down. And since we decreased the one, we had to increase the other. And then it might not fit, so we had to round. It is possible with rounding that it could, again, shift up, and you might have to renormalize a second time. And then you calculate the signs. In this case, it was a positive number times a positive number. Unfortunately, they picked the dash style when they did these slides. So, yeah, sorry, this is actually their slide. You know, you can tell when I'm using the book ones, they've got these here. This one's my own ugly slide. So, okay, so let's take a look at now taking the same thing, except we're going to do it in binary. So, you know, 1.00 times 2 to the minus 1 times minus, so this one's a legitimate minus, that's just the dash in the slide, minus 1.110 times 2 to the minus 2. So that's 0.05, because that's 1 times 2 to the minus 1, which is a half, so that's a half. And this one is minus 1.75 times a fourth, so that ends up being 1.75 divided by 4, 2 shifts over, and that gives you 4.375. So following the same set of rules, we're going to add the exponents. Minus 1 and minus 2 gives me minus 3. But realize that's what you want to do, but they're stored. Minus 1 plus 127 plus minus 2 times 127, which gives you minus 3 plus 254. You have to subtract the extra 127 to give you minus 3 plus 127. That is now, it's stored in the biased form. Then we have to multiply the significans, 1.00 from here, and 1.110 from here, and that gives us 9. That should actually be, that looks bad there. That's the little subscript. They evidently missed their subscript, so don't think we all of a sudden did something funny in the decimal range. It just gives you, as a result, 1.110 base 2. Imagine that subscripted. And then, so now they carry down the minus 3, just to show it times 2 to the minus 3, because they're about to renormalize. But in this case, it was fine. You didn't need to shift anything, so there was no change. Wasn't any over or underflow. We move on to the next. We have to round. There is no rounding in this case. So then we just take a look at the signs, and we just exclusive OR them. So in this case, it's minus 1 to the 0 power, minus 1 to the 1. So you got 0 exclusive OR 1, which gives you a 1. So the sign is minus. They just tell you multiply them, but we know that exclusive OR is what carries that out. So I'm going to do another example now. This one is kind of out of my little notes that's in there. Imagine we want to take 3.75 times 29.625. So what I've done first is just kind of convert it into the format. 3.75, that's 3 and 3/4. 3, that's 2 over, so 3/4. Normalize gives us 1.111 times 2 to the first. 29.625, this is 29, and 0.625 is 5/8, so 101 is 5, and it's in the 8th place, so 5/8. And then shift this over, gives you this times 2 to the 4th, because we have to shift it over 1, 2, 3, 4 places. Now we take this, we're going to multiply the significands. That's one. This one, so I just put in kind of standard multiply position. Here I am doing it without doing the shifts out. We just line them up as it goes in on the radix points, and I've done it here where I'm 1 times this, the 0.1 times those, 0.01 times that gives you this line, and the 0.001 times this gives you that line. So you're just shifting over. And then you add up. Right? So 1, 1, 2, so that's 0, carry a 1. 1, 2, 3, plus the carry gives you 4, 0. Right? So 4 is 0, 0, 1. So we got to carry over here. Right? That gives us 2, 0, carry 1. So now we have 2 carries here. So that's 2, 3, 4, 5. That's 1, carry 4. 1, 2, 3. Right? So that's 1, carry another 1. So now we got 2 carried into here. 2, 3, 4, 5. That's 1, carry a 1 all the way over here. 1, 2, 3, 1, carry another 1. So we got 2 carries. 1, 2 plus the 2 gives us 4. That's a 0. And that carry goes all the way over here because it's 4. 1, and then there's the carry out. So that's our number. And we note that this is really needs to be normalized, so I just write it with the radius point shifted times 2 to the first. We add the exponents to normalize, so I add this first, right? That's this, and then 1, 4, and the normalized value, plus the 127 for its encoding. Gives me 133, and that's what this number is, 128 plus 5. And then we write this into single precision. So in this case, both of these numbers were positive, so the sign is 0. There is our exponent. And then we take this lovely number here. Remember, we denormalize, or for the normalized ones, we don't record the hidden bit. So I'm just going to cover that up. And the rest of the number after the fractional part just gets copied down here. Anything past it, we just write zeros. I just put spaces in so it's easier to see that I have the correct number of digits. So here's another example. So I take x is 93.3125. This is that goofo thing that I did. You can see I haven't had a chance to fix it yet. So I actually take 93.125. Ignore that 3 is there. So 93.125, which is 93 and an eighth. We talked about how to calculate this last time, so that's the number we had calculated. And now we take our y, and I just give you a pre-encoded number y. So in this case, now we take our two numbers. This is 128, and this is 133. So we add them together and subtract the 127 because I'll get 2 of the bias codes. Now, I just note that 128 minus 127 is 1, plus 133 is 134. So it's an easier way to do it. Computers don't do that. They don't need shortcuts. They just blindly move ahead. But in our case, regroup to save yourself some time. So that calculates the exponent except for the possible shift. We're going to multiply 1 dot this times 1 dot this. But then we notice there's a huge number of zeros till a 1 appears here. So I'm going to do a little shortcut. And let me just show you this kind of shortcut trick. So this is a little aside here. And then we'll go back to the problem. Imagine I've got a number like this. 1 dot bunch of zeros. 1 dot zeros 1. Right? Okay, so just 1 zeros 1 dot zeros times. And then this one's small. Now this is small enough that it fits in the spaces. Now I can do this the old-fashioned way. Right? So I just take that number times this number. I've got them lined up on the decimal. This time I'm going to take the shifts out. So there's 4 here and 2 here. So I remove those 6 radix shifts. I can just write them as integers. I just do integer multiply. 1 times that puts 1 here. 1 times that puts a number here. 0 times this puts the number there. 1 times this puts the number there. And I add them. You can check and see. That gives me this number. I got to put those 6 shifts back in. 1, 2, 3, 4, 5, 6. There we go. And I put the radius point in. So you can see this is your traditional multiply answer. Now what I'm going to note here is every time there's a 1, you're copying. And you're copying to that location whatever is at the unit spot. So I find the 1 and I go, okay, line the radix point up just to the right of our number. So I just put the number I'm multiplying right underneath it. Every time I see a 1, I put the line up and I get the radix point of the second one aligned there. 1, go a little bit to the right, line the radix point up. And then I just carry them down. 1, 1, 0, 1. Right, next digit 1, 1. Right, so I just copy it down. The radix point to the original gets copied over. That's what that extra line is. That's where the radix point is located. If you look at this number, it's identical to this one. So if you see the kind of cute shortcut that's here, it can save you a little bit of time when you're calculating. I haven't noticed this as a good way to do it for computers, but it does work nicely for us as human beings. If you don't see it, you are welcome to do this lovely longer method. Whatever works for you works for me. So returning to the problem, since I've got this big gap and the other number fits within it, it just makes it easy. I just copy this number to where the first radix point is, and then I go to where the second one is, and I copy it again. And then I walk in, and it just turns out this is a really long number. So this comma is located where I run out of digits. So this is 23 digits right there. And it turns out that there's some of the number that goes out. So the first bit after that comma is a 1. So that means when I go to round, to make it fit in our thing, it's going to round up. So that means I'm adding a 1. So this bit will move over. 1 plus 1 moves over and I get 2. So that's why this shifts at the very end. Otherwise, it's an exact copy. And the leading bit, of course, is hidden, so it just disappears. There's no need to do any normalization because it fits nicely. We already calculated 134, so this is just 128 plus 6 gives me 134, and the sign of both was 0, so we have our positive. The signs are pretty trivial, so I'm not worrying about them here. Just make sure you do exclusive OR 0. Exclusive OR 0 is 0. Done. So I hope this helps. Now you have a good example or a couple examples of how to do multiply, and I will see you in class.